Hi, I'm Rob Weaver, and welcome to this executive overview of root cause investigation for CAPA. Today we'll explore this globally renowned methodology and its transformative impact across highly regulated industries. Root cause investigation for CAPA is a step-by-step technical problem-solving methodology, literally a roadmap to identify technical and systemic failures, enabling corrective and preventive actions, or CAPAs as we see in the title, that restore performance and prevent recurrence. Incorporating proven techniques from Six Sigma, Kaizen, TQM, and more, it's designed to guide professionals through defining problems, collecting data, testing causes, and implementing solutions effectively. It's not just problem solving, it's building a framework for continuous excellence. For the next few moments, think of an example of something critical that your organization would be measuring the performance of. Perhaps a piece of machinery or equipment, a product, a test method, even a work process. With this example in mind, let's imagine that over the past 3 months, we've been measuring its performance, and we're noticing every measurement is a bit different. Are you surprised? Probably not. We should expect some variation in performance, especially over an extended period of time. With 3 months worth of performance data collected, we should be able to calculate upper and lower control limits. And when we do that, we see that this performance variation is not only within those control limits, but we don't see any unusual patterns within those control limits. Very simply, this appears to be normal performance variation and not cause for alarm. Until now. Now we see a measurement outside that lower control limit. This is compelling data telling us that something, or perhaps some things, have changed. And this is not normal. I would refer to this as special cause of variation. And I suspect this represents to you a realistic scenario in which you would say, now hold on, this can't be ignored, this needs to be investigated. And we could take out a methodology like this one, follow that methodology, make the investments it's asking of us in the order of operations recommended. Our goal is to identify that change, which later on I'll be referring to as the technical root cause, or technical reason for this performance issue. And then once identified, we'll implement corrective action to eliminate that change. And if we're successful, I'm going to suggest that not only should performance improve, but it should go to a requirement or return to a requirement that needs to be met. And we should be able to measure with data that performance is now at that required level. Let me begin by emphasizing that I consider the first 2 steps in this methodology to be critical investments. Investments that many people skip in their haste to get the root cause. Before we break out a fishbone or a 5-why diagram to try and identify possible causes for this performance issue, it's first essential that we factually understand the problem itself. And that's precisely what the first 2 steps are designed to accomplish, the first being called define the performance problem. While there are several key investments made in step number 1, the 2 most important are describing the problem and process, or processes, being investigated. Let's start with describing the problem. This is literally universal to all methodologies, yet I find very few do this effectively. More often than not, the investigation procedure states, capture in as much detail as possible the issue that's occurring. Typically, the team starts with a few sentences of content. This might build into a few paragraphs, perhaps even a few pages. And then, rarely if ever does the investigation team refer back to the problem description once it's been captured. And it ends up being a check the box type of an exercise. I'm going to suggest we can do better, that we can structure the problem description in such a fashion that it becomes an actual, tangible tool that the team is actively engaging with throughout the bulk of the investigation. Before I introduce the tool itself, let me explain the theory behind the tool. In this methodology, we're going to deliberately describe the problem from 8 different perspectives. We'll begin with describing what this problem is, but we'll also describe what this problem is not. We'll then describe where this problem is occurring, but also where it is not occurring, when it's occurring and when it's not occurring. Finally, how much of a problem there is versus how much of a problem there isn't. Here's the theory. By describing the problem from these 8 different perspectives, we're beginning to establish what I like to call the scope of the investigation. Imagine for a moment that we're building a fence around this change, this technical root cause that we're searching for. The process begins with a well-rounded, well-thought-out problem description, as this helps us begin to establish the limits of our investigation. And that's what the box in the middle of my slide is intended to represent. If we've done this effectively, then when we start looking for possible causes in step number 3, we can be focused on causes that fall inside our scope. Conceptually, this should make our work easier. Then, as we move into step number 2, we're going to collect more data, hopefully in more detail, allowing us to narrow the scope of the investigation. And every time we do that, we make our jobs easier, as there will be less and less places we'll have to explore when looking for possible causes. And through this very systematic process of elimination, we'll narrow down the scope until we identify the technical root cause. Now that you understand the theory behind our approach to the problem description and the investigation more broadly, let me introduce the tool that will bring this to life, a tool called an is-not diagram. This tool contains a series of is and is not questions pertaining to what, where, when, and how much. This is by no means an exhaustive list of questions, but a proven starting point. The is questions help us begin to develop an initial problem description, and the is not questions help initially establish our scope. All answers captured will be treated as opinions that will collect data to substantiate and hopefully build upon in step number 2. This is also forcing us to break the problem description down into smaller, more manageable, bite-sized chunks of information that's going to be much easier to work with versus paragraphs or pages of information. The second main investment in step number 1 is to describe the process or processes being investigated. The best way to do this is with an old-fashioned process flow diagram, breaking down the steps in the work being performed, and with each step, identifying the key inputs being used in that work. Here's why. Chances are those involved in the investigation may have varying levels of understanding of this work, or some may not have experience in the work being investigated at all. So having a visual that everyone can refer to helps ensure those involved have a consistent understanding of the work being investigated. And as we'll see in step number 2, this high-level description of the process will better equip the investigation team to begin asking more detailed, poignant questions that better positions them to begin to narrow the overall investigation scope. So at a minimum, let's put together a process flow diagram encompassing the process taking place where performance deviation is first being observed. But depending upon the direction the investigation ultimately takes, other process flows may need to be developed and analyzed as well. Now that we have an initial problem description established through the is questions, an initial scope established with the is not questions, and a high-level understanding of the work we'll be investigating with the process flow diagram, let's move on to step number 2. As we acknowledged in step number 1, we should treat all the answers we captured in the is not diagram as opinions. Here in step number 2, our focus is on the facts. We're going to take the is not diagram and use it to build a data collection plan. The goal is to collect 2 different types of data. First, we'll collect data to determine if these initial is not answers are factual or not. This will give us not only a factual problem description to move forward with, but also a factual scope to look for possible causes within. Pretty good. But is that good enough? Sometimes, sure, okay? Sometimes simply verifying our initial is not answers will sufficiently establish and narrow our investigation scope. However, more often than not, we're going to have to ask additional follow-up questions to many of those is not answers to get a better, more detailed understanding of what's going on. I'd like to take this initial factual scope and narrow it down to something a bit smaller and more refined. And having the process flow diagram is going to better equip us to think of more detailed follow-up questions. The overarching goal at the completion of step number 2 is to have a factually based problem description using the is not diagram, and for it to be more detailed than it was at the end of step number 1, thus narrowing our investigation scope so we can be more laser focused when identifying possible causes. Now that we've established and narrowed the investigation scope, I think it's appropriate to begin identifying possible causes. My primary message here would be to leverage a variety of different techniques to accomplish this. If the fishbone diagram is your tried and true go-to tool, of course use it. However, I would strongly encourage you to go beyond the fishbone, as several other excellent techniques can also be leveraged. For example, we could put together a timeline of changes relevant to the investigation, as any change, no matter how seemingly small or seemingly insignificant, is going to carry with it at least some level of inherent risk of creating an entirely new problem. If a risk analysis exists, such as an FMEA or failure modes and effects analysis, I'd strongly recommend reviewing it, as it seems at least possible that the individuals who conducted the risk analysis way back when perhaps identified this particular issue being investigated as a potential failure mode. Process flow walks or GEMBAs can be conducted to identify causes. General brainstorming sessions can be leveraged. And my personal favorite, we can leverage the is not diagram, going through each set of facts asking, is there anything different about this is fact compared to the corresponding is not fact? Documenting any differences identified and treating them as possible causes. We can then follow up by asking, has anything recently changed with this difference, which could further refine the possible cause or perhaps even generate an entirely new possible cause? But our goal, as we finish step number 3, is to have a robust list of possible causes. This is where the rubber meets the road. We're going to test each possible cause against the facts in the is not diagram by asking, if X is the cause, how does it explain each set of is and is not facts? Now, there are a few possible outcomes. Scenario 1, a set of facts does support a possible cause, and we keep testing. Scenario 2, a possible cause does not support a set of facts, but a reasonable real-life assumption can be made to explain how that set of facts could still support the possible cause, and again, we keep testing. And then scenario 3, a set of facts does not support the possible cause, and we're not able to make a reasonable real-life assumption. In this case, the possible cause is eliminated. In my experience, most possible causes will not pass this facts test, and this is good. We've got to narrow down our list of causes, and most causes that do pass this facts test are probably going to have some reasonable real-life assumptions attached to them that need to be vetted out, which we'll cover in step number 5. A quick review of the past few steps. In step 3, we generated a robust list of possible causes. In step 4, we tested those causes against the facts in the is not diagram, most likely eliminating many of those causes. Chances are any causes that did preliminarily pass the facts test had some reasonable real-life assumptions attached to them. So here in step 5, we'll begin by collecting just a little bit more data regarding those assumptions to see if they're based in reality or not. If any of these assumptions are proven false and not able to be replaced with new assumptions that can be vetted out, well, those possible causes are eliminated as well. At this point, any remaining causes have fully passed the facts test, and I suspect there won't be more than a few at most. Now is the time to conduct experiments on those remaining causes, because when, through an experiment, the problem can be controlled, moved, manipulated, turned on and off like a light switch, that is compelling evidence that a technical root cause has been identified. At this point, I recommend taking a step back and reflecting on this journey by leveraging the second most popular root cause analysis tool out there, the 5 whys. I think it's now appropriate to ask, why did this technical root cause occur? I also think it's appropriate to ask, why wasn't this technical root cause detected earlier? Here's the idea. I'm trying to determine if we have any systemic root causes, also commonly referred to as contributing causes or environmental causes, that leave us vulnerable to similar issues in the future if left unaddressed. For example, was there a failure in our quality system that allowed this technical root cause to occur? In design control or validation, or even our communication channels? By identifying and addressing systemic root causes, we'll be able to better prevent similar issues from arising in the future. One of the biggest mistakes we find people make is to latch on to the first corrective action idea that comes to mind and start charging forth with it. Before selecting a corrective action, I think there are some intelligent questions that we can be asking to better inform the direction that we ultimately take. First, we should determine where the root cause is stemming from, which ultimately will be either human error or excessive variation. If human error, we should first consider the possibility of eliminating the issue entirely. Wouldn't you agree that would be the best option? And if that's not an option, then consider strategies to reduce overall occurrence. If root cause is stemming from excessive variation, well, we're going to have to involve those that are highly trained in variation reduction and optimization techniques to target output against performance requirements. But upon determining what we'd like the corrective and/or preventive actions to be, we need to consider risk. Okay? In other words, what could go wrong with these actions, as well as what can be done to prevent that risk from ever occurring. Next, we need to establish a control plan to monitor the effectiveness of these actions or the lack thereof. Finally, we need to document acceptance criteria. What should the outcome of these actions specifically be? Here we implement our corrective and/or preventive action plans and measure effectiveness through those control plans that we mentioned in step number 6. If we find we're able to make some improvement but still have a performance gap, let's more closely scrutinize the plan itself, making it more robust or putting tighter controls in place to ensure complete implementation. If we've done everything possible with the plan, made some improvement, but still have a gap, then our data is telling us, well, there must be more than one technical root cause. So we continue to follow the process, flushing out new possible causes, testing them against our facts, verifying assumptions, and experimenting until that secondary technical cause is flushed out. Then developing and implementing corrective and/or preventive actions and measuring results against requirements that need to be met. And if we are successful, then 1, this technical issue has now disappeared. 2, no new issues are arising as a result of our actions. And 3, the problem is staying corrected. Or if it does return, that our control plans give us earlier detection the next time around. Looking ahead, our commitment is to embed this methodology deeper into organizational cultures, empowering teams to innovate and enhance performance continuously. Thank you for joining me in this overview. Root cause investigation for CAPA is not just a methodology, it's a mindset that fosters resilience and delivers excellence. Connect with us today to learn how we can revolutionize your approach to problem solving and innovation.